Okay, so hello everyone. So today Volker Stern is our guest from the University of Virginia, and he's going to tell us a story about spans. So, okay.
So thank you very much, and thanks for the invitation to speak. As Cihan said, I am going to be telling a story about spans. So there's this somewhat ubiquitous construction that shows up all throughout a lot of seemingly disparate branches of mathematics. And one of the threads that has gone through my research over the past 4 or 5 years relates to this span construction. And I'm going to try and tell that story up to the present day. So let's begin just by saying what the main object of study is. And the main object of study is categories of spans in some category C. Now, this is actually kind of a bad start because it's the first sentence of my talk, and already I'm telling a bit of a lie. So I will explain in due course what the lie is and why this is a bit of a lie. But for the time being, just bear in mind that some of this is a little heuristic. So the basic idea is that we need to start with some category that has some very mild properties placed on it. So it has to have pullbacks and a terminal object. So for example, we could take the category of topological spaces with continuous maps, and there the pullback is the fiber product and the terminal object is the one-point space. Or sets and functions, and there the terminal object is the singleton, and again the pullback is the fiber product. Finite sets, in which case it's the same as with sets. Or slightly more complicatedly, one could take the category of groupoids and functors, and there one has to reinterpret pullback in a somewhat homotopical sense, but one can also do the construction strictly using the strict pullback of categories. And there are many others. So a lot of the categories that show up regularly in category theory will have these two properties. They're very mild. And I should also say, all of the constructions that I'm going to discuss today can be illustrated more or less entirely in the context where C is just the category of sets and functions. And so if you're more comfortable in that setting, I encourage you to just think of sets and functions where the pullback is the fiber product and the terminal object is the singleton. So given such a category that has these two mild properties, we're going to construct a category span C. And since I'm asserting that this is a category, I need to tell you what its objects, morphisms, and composition are. So the objects of this category, which I'll label X, Y, and Z, are just going to be objects in the original category C. So this construction that we're doing is not changing the objects. And so it's going to have to change the morphisms. A morphism from Y to Z is going to consist of an object, F in C, and then two morphisms in C. Which I'm labeling S sub F and T sub F for source and target. And this sort of a diagram in C is what's called a span. And F is sometimes referred to as the roof of this span. So our morphisms are going to be these odd diagrams in C. And already there are some interesting properties that one might notice. So for instance, it's possible to read a span backwards and still get a span. So switch the source and target maps. And so there's some sort of duality that lives on this category. And then if I have two morphisms, F from Y to Z and G from X to Y with their source and target maps, I can compose them. And the way I do this is I use these properties that I asserted the category needs and form the pullback. So this pullback or fiber product, F cross G over Y. And then this is the pullback in the category C, and I can compose down the left-hand and right-hand diagonals to get these new structure maps, the source for F composed with G and the target for F composed with G. And so this is effectively the category span C. But here's where the lie comes back. This composition isn't unique. So category theoretically, there are many possible objects that we can put in for this fiber product here. In fact, the fiber product is only uniquely determined up to unique isomorphism that commutes with these two red projections to F and G. And so what this means is this can't really be a category because we don't have a unique composition. What it really is instead is if we start with a one category, we can push up the ladder of categorification to get a two category. And since I know that there's been this seminar on higher categories here, let me say now that we can actually put all of this into a much more general framework and say that if C is an infinity category that satisfies the infinity categorical versions of these two properties, then we can get an infinity category out of this. So since I'm asserting that this is now a two category, I need to tell you what the two morphisms are. So if I have two spans, which are one morphisms from X to Y, F and G, then a two morphism is just going to be another morphism in C, F, that goes from the roof of the first span to the roof of the second span, and commutes with the source maps and the target maps. And for most of this talk, it will be entirely fine to assume that F is an isomorphism. At the very end, I'm going to talk a little bit more about the non-invertible morphisms, but for most of the talk, it's fine to just think of this as, say, a 2-1 category where all of the two morphisms are invertible. So now we come to the nihilistic question that one always has to ask, which is, why care?
Can I ask a question before you move on? Sorry.
Yes, of course.
It's like you have a condition on C saying that it has a terminal object. Is this necessary, or how do you use that?
So this is necessary because I eventually want to discuss the product, just the Cartesian product in this category. So you can multiply two spans object-wise, where you multiply the objects and multiply the roofs and get a new span. And this provides what's called a monoidal structure on the category of spans. But to do that, to get products out of pullbacks, you need a terminal object, because the pullback over the terminal object is just the product.
Is this often assumed when you introduce spans, or is it like in the general condition?
So
span definition is like products is an extra thing, or you always want products there?
In practice, most of the settings where one is interested in spans do have products, because even categories where pullbacks are very badly behaved tend to have products. So think of the category of smooth manifolds. Here, pullbacks are not hugely well behaved because you need transversality conditions to get intersections that are smooth manifolds. However, if I give you two smooth manifolds, you can take their product. So in practice, most categories where one considers spans will have the terminal object, or at least will have products. Now, it's worth saying that one can actually do span constructions, as we'll see, in categories that are not quite even as well behaved as this. But generically, I'm taking these to be our assumptions because they make the exposition smooth.
Okay, thank you. Thank you.
Yeah, thank you. So, going back to this question, why should we care? Well, the main reason we care is that this construction shows up in a bunch of seemingly unrelated branches of mathematics. So to begin with two more basic examples, we have partially defined functions and relations. And so we can view a partially defined function from, say, a set X to a set Y as a span, where U is an injective map, and F is any map. So it's a span where the left-hand morphism is an injection. And if we have two of these things defining partial functions, then they define the same partial function precisely when there's a two isomorphism between them. So for instance, we could have two injections that define the same subset of X, but that technically use different sets, U and V. And so partially defined functions can be viewed as isomorphism classes of spans. And the composition here really functions via the pullback, because if you take the pullback of an injection against another function, you will get an injection. And then on the other hand, we can view a relation as a particular kind of span, where a relation is just a subset of a product of sets. And here, the composition differs slightly from the composition in the span construction, although there's actually a fairly subtle relation between them. So here the composition is that one takes this pullback and then takes its image in the product of sets that one is interested in. So presses it down so that one actually gets a relation. On a more complicated note, there are natural variations of this construction that appear in topological quantum field theory and symplectic geometry. So in topological quantum field theory, we can view a cobordism as a cospan. And because I'm a category theorist, the word co always just means reverse the direction of morphisms, except when it appears in the word cobordism, where it means nothing. So if I draw this, say, pair of pants cobordism, then this is a cobordism that goes from two circles to one circle. And we can view the inclusions of the incoming pair of circles, the incoming boundary, as one leg of the span. And the inclusion of the outgoing circle, this one circle, as the other leg of the span. And so this can naturally be viewed as a span of, say, smooth manifolds or topological spaces. And the composition, at least as topological spaces, is the push-out, the dual of the pullback. So what this means is we take a disjoint union and then we glue. And a boundary-preserving diffeomorphism or homeomorphism is going to be a diffeomorphism or homeomorphism that commutes with these boundary inclusions. So topological field theory really does fit into this span framework or cospan framework in a very natural way. It is worth commenting that here, one actually has to decorate the spans with a little bit of additional data. And the reason for this is that to ensure a good gluing of smooth manifolds, one needs to choose, for instance, germs of collar neighborhoods for the incoming and outgoing boundary so that the gluing provides a canonical smooth structure. Now, on the other hand, in a very different way, in symplectic geometry, a variant of the span construction comes into being, again, seemingly unrelatedly. So Alan Weinstein in the 70s and 80s defined a more general notion of a morphism between symplectic manifolds. So if we have symplectic manifolds M and N, then a Lagrangian correspondence from M to N is what I've written as L subset of M bar plus cross N bar. So M bar is just M equipped with the negative of the symplectic form of M, and L is a Lagrangian submanifold. And the reason that Weinstein suggested studying these things, at least initially, is that in the special case where M and N are symplectic manifolds of the same dimension, and there's a symplectomorphism from M to N, the graph of that symplectomorphism is a Lagrangian correspondence in this sense. And so this is a generalization of the morphisms that were typically studied in symplectic geometry up to that point. Now, these can also be composed. If I have L1 from M0 to M1 and L2 from M1 to M2, then I compose these in much the same way that I suggested composing relations. I take a fiber product, and then I take its image in M0 cross M2. So it's also worth noting that one needs a bunch of conditions to make sure that this composition is well defined. And in particular, one does need transversality. Now, part of the reason that these symplectic these Lagrangian correspondences are important is work of Verheim and Woodward in the 2000s, which said that the Fukaya-Donaldson category, a higher categorical invariant of symplectic manifolds, is functorial in Lagrangian correspondences. So for those of you familiar with this framework, what this means is given a Lagrangian correspondence, one gets a functor of Fukaya categories associated to that Lagrangian correspondence. And this assignment of A infinity functors respects composition of Lagrangian correspondences. Now, to put this in the framework of spans, there is a derived version of this whole story within the derived symplectic geometry framework developed by the PTVV papers. So in the 2010s, Kalak and Haugzang described the derived version of this Lagrangian correspondences framework, where now one replaces these symplectic manifolds with some derived version, replaces the pullback with the derived pullback, and replaces a Lagrangian correspondence with something like a shifted Lagrangian correspondence. And what happens in this case is one gets nicer formal properties. So to compute intersections, of course, one still needs to isotope submanifolds until they're transverse and then take intersections. But within this higher categorical framework, the derived version of this really is a subcategory of an appropriate infinity category of spans in shifted symplectic structures. And then the final version of this span construction that I want to discuss is the one that motivates some of my own work, and is that of categorified algebras. So there is a functor from spans of sets to Q vector spaces. And the Q here is sort of arbitrary. I could put other fields, say the real numbers or the complex numbers here, but it will work just fine with the rationals. And there's this functor that goes from spans of sets to Q vector spaces, and it sends X to the vector space of maps from the set X to Q. And then it will send a span to a map of vector spaces. So if we have this span, F with structure maps sigma and tau going from X to Y, then this will take as input a function from X to Q, and then it will restrict it along sigma. So take the composite F of sigma to get a function on F, and then sum over the fibers of tau to get a function on Y. And it's worth noting that once again, this actually takes as input some restricted span category. One needs finiteness conditions on the fibers to guarantee that this sum is well behaved. But in principle, this is what is going on. And there are a variety of finiteness conditions that one can put that will ensure that this is in fact functorial. And in 2009, Baez and Dolan upgraded this construction. And this was as part of what they called their groupoidification program, which was an attempt to lift a number of constructions in mathematical physics, in particular Fock spaces and Feynman diagrams, to a categorified setting. And so they defined a variant of this functor where one replaces the category of sets with the category of groupoids. And now to get this vector space, they just take functions on the isomorphism classes of a given groupoid. So this sends a groupoid to maps from its isomorphism classes to Q. And the functoriality is a little more complex. So this sum over fibers is effectively introducing cardinalities of fibers as part of the data of this functor. And they replaced this cardinality with what they called groupoid cardinality. And this effectively divides the cardinality by the size of automorphism groups in the groupoid, so that one gets a cardinality that actually respects groupoid quotients. So this provides an upgrade of this functor that goes from some restricted category of spans of groupoids to Q vector spaces. And in 2014, Galvez, Carrillo, Koch, and Tonks showed that one can lift what they called incidence coalgebras. So these are combinatorial algebras that are used in combinatorics and number theory to coherent coalgebras in spans of groupoids, and showed that you could actually do some rather interesting computations at what they called the objective level, the level of these coherent algebras in spans of groupoids. So that is the theme that I want to pick up as the first component of our story: algebras in spans. So to try and simplify the understanding of this coherent structure that shows up in spans, because spans are a two category, so we need a complicated system of isomorphisms representing associativity. What I'm going to do is run through what an associative algebra is, first in vector spaces and then in spans. So an associative algebra is going to consist of three pieces of initial data and then some additional coherence conditions. So firstly, we need an object that carries the vector space structure. So this is a vector space V, or in spans, an object X1. And I should say, all of the notations that I'm going to give in spans with these subscripts are quite suggestive. And in a couple of slides, we'll see what they're suggestive of. So then we need a multiplication. And this multiplication is going to take the form in vector spaces of a linear map M from the tensor product of V with itself to V. And this is because the tensor product is the canonical way of combining two objects in vector spaces to get a third object. It's the symmetric monoidal structure on vector spaces. And as we saw earlier in response to this question about terminal objects, there is similarly a way of combining objects in span C to get a new object, namely the Cartesian product. So a multiplication in span is going to take the form of a map from x1 cross x1 to x1. And again, I'm giving some suggestive notation to all of these. The roof of this span is going to be called x2, and the three maps involved in this span are going to be called d0, d1, and d2. And as a shorthand for this span, I'll write mu. And then finally, we need a unit. So in vector spaces, this takes the form of a map U, a linear map U, from the base field K to V. And the reason that K is the right object to put here is because when you tensor K with any other vector space, you get that vector space back. And in spans, there is an object that plays a similar role, namely the terminal object, which I'll denote by an asterisk. And so the unit in spans takes the form of a map or a span from the terminal object to x1. And again, there's some suggestive notation. I'm writing x0 and s0 for the data of this span. And I'll denote this span by epsilon. So let's keep this basic data that we need for an associative algebra up in our top right-hand corner. And now let's turn to associativity itself. In vector spaces, this takes the form of an equation. If we compose the multiplication with the multiplication tensored by the identity, that has to be equal with the composite of the multiplication and the identity tensored with the multiplication. So this says if we have three elements of our algebra, A, B, and C, then if we multiply A and B and then multiply that result with C, we get the same thing as if we multiply B and C and then multiply A with that result. And if we want the same equation or the same principle to hold in spans, we first need to compute these two composites. So here, I'm taking mu tensor the identity. So here we have x2, which goes from these two copies of x1 to this copy of x1, and then the identity, which is just the span whose legs are identity maps from x1 to x1. And here I have mu, so I'm going to compose mu with mu times the identity, and this should give us the left-hand side of this equation. So I take the pullback, and I get a new object that I'm suggestively calling x3. And then I compose the sides to get mu composed with mu times the identity. And we can do the same thing for the right-hand side of this equation. Now I have the identity tensor, or times mu and mu. And now I form the pullback, which I'm not giving a suggestive notation because this notation is going to disappear pretty quickly. And we get mu composed with the identity tensor mu. And now, if we just followed the example of vector spaces, we might want to require that these two are equal. But unfortunately, this is a very silly thing to want in spans, because in spans, these composites aren't actually uniquely defined up to equality. They're uniquely defined up to isomorphism, which means we can't require that they're equal. It just doesn't make sense. So instead, we require that there's a specific two isomorphism that goes between them. And I'll call this two isomorphism temporarily alpha. And from this two isomorphism, we get a bunch more information. Namely, for instance, maps from x3 to x2, d0, d1, d2, and d3. And we can similarly explore the unitality condition, which I'm not going to walk through in this way just because there's not really enough time. And similarly, we can also look at higher associativity. So I could compose the multiplication with another multiplication to get something that goes from 4 copies of x1 to a copy of x1. And similar relations are going to have to hold there. So we now have some data that emerge from this associative algebra in spans, and we can reformulate that. So an A-infinity algebra, and that just means an algebra that is associative up to this system of isomorphisms that I started to construct, consists of some objects, x0, x1, x2, x3, and so on. So you'll have an x4 representing a 4-fold multiplication, and so on and so forth. And then a collection of morphisms in C that I've labeled D's and S's. And so this is just a simplicial object in C. So all of this coherent data that goes into this algebra comes together to give us a simplicial object, but we also need some conditions. So why do we need some additional conditions? Well, if we go back to this previous diagram, you'll notice that this square, for instance, had to be a pullback square, which is not necessarily guaranteed by an arbitrary simplicial object. So we get a simplicial object in C plus conditions, and these conditions are of the form that certain squares have to be pullback. So first off, there's this collection of squares for any n greater than or equal to 2 and any I and j between 0 and 2. And these govern coherent associativity. So in the case when n is 3, I is 0, and j is 2, we get that x3 should be the pullback of x2 and x2 over x1. And if we go back to this first pullback condition here, we see x3 is a pullback of x2 and x2 over x1. So we get that coherent associativity amounts to certain pullback conditions, and then the unitality conditions that I didn't go through amount to a different set of squares being pullback. So these two sets of squares being pullback are the conditions that we need. And these have already appeared in the literature. So Dyckerhoff and Kapranov in 2012 were interested in categorified Hall algebras and the S-dot construction, and called these conditions the two Siegel conditions. And the reason, since I know that there's been this seminar that's covered some Siegel spaces, the reason that they called these two Siegel conditions is they generalize the usual Siegel conditions, which they called the one Siegel conditions. And the way that they generalize them is that any Siegel space is a two Siegel space. Now, these conditions were also independently developed by Gavef, Carrillo, Koch, and Tonks when they were studying these incidence coalgebras, these categorified incidence coalgebras. And they called a space, a simplicial space satisfying these conditions, a decomposition space. So there is some relation of these conditions to algebras in spans. And the first theorem of mine that I want to discuss is making this precise. So I'm stating this in its full infinity categorical generality. If C is an infinity category with enough limits, and by enough limits, I mean has pullbacks and a terminal object, then there is an equivalence between A infinity algebras in spans in C and two Siegel simplicial objects in C. So simplicial objects in C that satisfy these conditions. And the power of this theorem is really that the thing on the left-hand side is quite complicated to write down. And the thing on the right-hand side is often quite easy to write down. And the other thing that this tells us is that these two Siegel conditions, which were developed as a helpmeet to try and understand some categorified algebras, actually exhaust all of these categorified algebras. All of these can be written down in this simple form of a simplicial object that satisfies some conditions. Now, I also proved a generalization of this theorem. Namely, one can consider what are called Calabi-Yau algebras, which one can think of as an infinity categorical of a symmetric version of a symmetric Frobenius algebra. So what this means is you have an associative or A infinity algebra, and then you have a trace that is non-degenerate and satisfies a cyclic permutation condition. And similarly, there's a category lambda called Kahn's cyclic category because it was developed by Alain Kahn in the 80s. And this amounts to taking the simplex category and adding the cyclic shift automorphisms of N to the simplex category. And these Calabi-Yau algebras show up in a number of contexts. As we'll see, they show up in infinity categorical topological field theories, but they also take their name from a construction in algebraic geometry that is somewhat related. And we can upgrade this theorem to say that Calabi-Yau algebras in spans of, in C are the same thing as two Siegel cyclic objects in spans in C. Now, the point of this upgrade and the interest of this upgrade is that it allows us to make a stronger statement using a theorem of Lurie from On the Classification of Topological Field Theories. So on the classification of topological field theories, Lurie shows that Calabi-Yau algebras classify a certain type of topological field theory. So as a corollary, we see that open-oriented two-dimensional topological field theories in spans are equivalent to two Siegel cyclic objects in C. So once again, the power of this theorem is that it reformulates complicated data in terms of more simple data. Namely, a topological field theory in an infinity categorical sense can be quite hard to write down, but very often two Siegel objects or cyclic and simplicial objects are easier to write down. So let me just give one example of the corollary to give a flavor for how this might work. One can take a topological space X and a base point little x in that topological space and form a cyclic space which has as its objective 0 simplices, just the 1-point space, 1 simplices, the loop space of X, 2 simplices, 2 copies of that loop space, and so on and so forth. And here the structure maps are given by forgetting loops, concatenating loops, and taking constant loops. And this is in fact Siegel. This is a Siegel space. And so it's 2 Siegel. So by the corollary, we should get a topological field theory out of it. So if I take an open cobordism that has 2 incoming intervals and 1 outgoing interval, so this is what's sometimes called a flat pair of pants, and a free boundary labeled in red, then this topological field theory will assign to this cobordism, well, it will assign to the object I, these 2 incoming intervals, the space of maps from I to X that send the intersection with the free boundary to the base point. And similarly, it will send the outgoing interval to the space of maps from O to X that send the intersection with the free boundary to the base point. And the roof of the span will be maps from the whole cobordism to X that send, again, the free boundary to the base point. And we can reformulate on objects a rather simpler version of this. So this is maps from 2 intervals to a space that send the endpoints to the base point. So this is just a pair of loop spaces. And this is maps from 1 interval to X that sends the endpoints to the base point. So this is just the loop space. And so we get a topological field theory that has showed up at various places in the literature previously that comes from this relatively simple simplicial object. And these results that I got in 2019 can be further extended. And so somewhat to my surprise, I ended up recently starting to work with a symplectic geometer and a mathematical physicist, Contreras and Rajan Mehta, who are interested in studying topological field theories in variations of Lagrangian correspondences. So both in the 1 and 2 categorical senses and in this derived infinity categorical sense. And so they're interested in some additional algebraic structures in spans as a first step towards this goal. And so a theorem that we now have proven is that we can extend these equivalences from my previous work to give equivalences that relate commutative and Frobenius algebras in spans to more 2 Siegel objects that now have slightly different structure. So instead of the simplex category, we now have finite pointed sets corresponds to commutative algebras. And this is because in finite pointed sets, there are symmetric group actions built in, which one needs in the commutative case. And then there's a more complicated gadget called the paracyclic category that corresponds to Frobenius algebras. And this work is ongoing, and we're working on the infinity categorical version, and I already have a sketch of the proof in that case. And then, as I said, the eventual goal is Frobenius algebras and topological field theories in Lagrangian correspondences. So in this symplectic geometry world. Now, from these results on algebras, there's actually an interesting connection to be made that relies on another theorem, this time by Tashi Walde from 2017, who showed that there are other types of data that are equivalent to these 2 Siegel spaces. Namely, if we take 2 Siegel objects in the infinity category of spaces, then on the one hand, 2 Siegel simplicial objects are the same thing as invertible infinity operads. And don't worry too much about the word invertible, it's going to disappear pretty soon. And 2 Siegel cyclic spaces are invertible cyclic infinity operads. So if you put this together with my theorem, this tells us that invertible infinity operads are the same thing as algebras, A-infinity algebras, in spans of spaces. And similarly, cyclic invertible infinity operads are the same thing as Calabi-Yau algebras in spans and spaces. So the big takeaway from this, from these two theorems, is that there's some close and profound connection between operads and algebras in spans. So let me back up for a moment and say, what is an operad? What do I mean by that? And why is it important? Well, operads are a way of parameterizing algebraic structures in some arbitrary category. So in sets, there are some straightforward examples: associative monoids, commutative monoids, vector spaces. And one can get more complex. So for instance, A-infinity algebras and En algebras, especially in spaces, are one of the motivating examples that first motivated the definition of operads. And May's recognition theorem that tells us that n-fold loop spaces are the same thing as a certain type of up to homotopy algebraic structure called an En space is phrased typically in terms of operads. But I'm going to use the example of vector spaces to explain what I mean by an operad. So let's look at the operad of K vector spaces, and let me tell you what information this operad needs to remember. We want to remember all possible operations from the n-fold product of V to itself that would come from a vector space structure. Now, I should say here, V is a dummy vector space. We just want to remember the type of operations that we would get regardless of what vector space we chose. So if you plug in any V, you should get operations of the form that we're going to list. And I'm going to call such an operation from the n-fold tensor product of V to itself an n-ary, the n-fold product of V to itself, an n-ary operation. So we need to remember the zero-ary operations that come from a vector space structure, and really there's only one. There's the one that goes from the point to V that remembers the zero object, the zero element, the zero vector, if you like. And we can draw this as a tree, which is the conventional way of representing operations in an operad. And so we draw this as a tree that has no leaves because it has no inputs, no copies of V as inputs, and one root because it has one output V. And we'll label it by 0 to remember what it's doing. And then we have one-ary operations. And here we get a one-ary operation with scalar multiplication from V to V for every element of the base field. And we'll draw this as a tree with one leaf, one input, and one root, one output, and label it by that scalar. And similarly, our two-ary operations will go from V cross V to V and will be linear combinations, so indexed by two elements in our base field. And we'll draw these as a tree with two leaves that are labeled by the two scalars involved in the linear combination. So we need to remember all of these operations, and then we need to remember how they compose. So if I compose the two-ary operation, the binary operation given by lambda and mu, with the binary operation given by gamma and delta, the fact that scalar multiplication distributes across addition in any vector space means that this has to be the three-ary operation with labels lambda, mu gamma, and mu delta. And when we're thinking about operads, we compose at a specific input. So I'm plugging this one binary operation into the other binary operation at its second input. And so to indicate that that's what I'm doing, I would write this composition as compose with a little subscript 2 on it. And as another example, I could plug the zero-ary operation into a binary operation. And here I get a one-ary or unary operation that's just labeled by mu because 0 kills off lambda. And again, this is the composition at the first input, and so I would write the composition with a little subscript 1. And the last piece of information we have to remember are permutations. So I can permute the inputs to one of these linear combinations. And all that does is gives me one of the other binary operations where now I've switched the order of these labels. So the data of an operad, remembering, for instance, everything one can remember about vector space structure, is, well, a set of n-ary operations for every n greater than 0, symmetric group actions that we think of as permuting the inputs, and compositions that say if I plug an n-ary operation into an m-ary operation, I get an n plus m minus 1 ary operation. And then there are some compatibility conditions, and I should say, these compatibility conditions would take a very long time to write out. However, if you were to spend 2 hours just playing around with trees, the compatibility conditions that you would come up with are almost guaranteed to be the right compatibility conditions for the definition of an operad. It's just the things that have to be true if you're plugging trees into one another. And there are two generalizations of this. Firstly, one can take an operad in a symmetric monoidal category. Think topological spaces where you might have a space of operations, or chain complexes where you might have a chain complex of operations. And so now instead of a set of operations, we have an object of operations. We still have symmetric group actions, but the compositions now go from the appropriate monoidal product. So that could be the tensor product of chain complexes or the Cartesian product of topological spaces, subject still to compatibility conditions. On the other hand, we can also generalize operads to many object versions. So with a vector space, there's only one object that carries the structure, that object V. And all of the operations take V as both inputs and outputs. But if we wanted to study, say, a combination of an algebra and a module, well, one needs to remember two different possibilities for inputs and two different possibilities for outputs. And so we might want to have a multi-object version of an operad, which nowadays is often called a colored operad, although for a long time they were called multi-categories or symmetric multi-categories. So this connection between operads and algebras in spans actually turns out to have been observed by Day and Street, who said in the early 2000s that a colored operad in set is the same thing as a lax algebra in span set. And so I have to say, I was a little bit disappointed when I first saw this observation, because I thought that I might be able to get a somewhat interesting paper out of this one categorical version of the observation, but it turns out that no, it's already in the literature. So what do I mean by a lax algebra? Well, a lax algebra in span set is very much like one of these A infinity algebras. So now I'm writing O to emphasize the connection with operads, but remember, we had this diagram where we had, on the one hand, a pullback of x2 and x2 over x1, and we had this x3. And we wanted to require that these were isomorphic in a canonical way. And that was our A infinity algebras. Now, instead, this word lax means that we forget that things are isomorphisms and just remember that there is amorphism between them. So some not necessarily invertible morphism connects these two. And one can already, just looking at this diagram, sort of see how this might connect to operads. Namely, this map, alpha, looks a little bit like an operatic composition. It's going to take a 2-ary operation and a 2-ary operation and give us a 3-ary operation, just as the composition that we wanted in operads did. Now, with a little bit of work and a result of Haugseng from 2015, Rune Haugseng, it actually turns out that this generalizes pretty immediately to infinity categories. Namely, a colored infinity operad is the same thing as a lax algebra in spans of spaces. So this is the story for operads, but then what about this cyclic picture that comes in? Well, my ongoing work is, or one thread, I should say, of my ongoing work is the conjecture that lax Calabi-Yau algebras in spans are the same thing as cyclic infinity operads. And cyclic infinity operads come up in the study of topological field theories, but also in the study of, say, cyclic homology. And so this would be a useful piece of data to reformulate. And as part of this, I'm working on a new model for cyclic infinity operads, which is also a little bit better suited to studying algebras over cyclic infinity operads, and the relation to other models. So to let me briefly recap, this story that we went through started from this question of categorified algebras, trying to lift algebraic structures to spans where one can use homotopy coherent technology to study combinatorial algebras. And then in classifying algebras in spans, we saw that there's this profound relation to conditions on simplicial objects, these two Siegel conditions. And from this profound relation, it follows that there is a connection with operads and higher operads. And so this story begins with categorified algebras, but it ends with a connection between these three seemingly unrelated objects, these cyclic operads, these two Siegel spaces, and these algebras in spans. So that is more or less what I wanted to say. Thank you very much for your attention. And if there are any questions, I'd be happy to answer them now.
Okay, thank you, Volker.